Are you guys on? So we already I was actually.
That's good. Can you hear me? All right, I think we'll get started in a few minutes. So if everyone wants to grab another drink or grab some food and take a seat, we'll get started shortly. And for everyone online, this is a notice that we'll start shortly. Yeah, this works. This all works, right? All right, thanks everyone for coming. Great to see everyone, and great to see some old and new faces. This is the first in-person event that CTBUH has done, so it's super exciting. We have it's the first one we've done in 2 years. Excuse me. So we're super excited to be back in person, and very thankful that TT allowed us to host in their office. This is also a new office for TT, and the first event we as New York CTBUH has hosted in TT. So just a few words before we give it over to Rob and Sergey. I know you're here to hear them talk and not me. So that's fair. I just want to give a quick intro on CTBUH in general. The New York chapter is kind of a group of professionals in the AEC industry. We have developers, designers, engineers, and architects. And we host events like this, basically, in-person events around a certain topic, like AI tonight, or just project-specific events, and sometimes including building tours as well. And just to give you a little teaser, this is over here, teaser of what we have done in the past. Just a few photos of some building tours and presentations that we did in 2019, the last in-person event that we did. And so if you are interested in being more involved with the chapter, we'll be having a board meeting and a planning meeting in September. So if you are interested in being a part of the group, please come and meet some of the individuals that are on the board and see where you can make an impact in the group. Just grab me at the end of this, or you can email us as well if you want to get in contact. So with that, I'll give it up to Rob and Sergey for the talk. I'll just hold it.
I'll put it up there in a sec. We're going to do intros really quick. Thanks, Nick. And thanks everyone for joining. Today we're going to talk about artificial intelligence, machine learning, and how it can be applied, and it is being applied to structural design. Before that, I just want to do a couple of quick intros. So I'm Rob Otani, Chief Technology Officer at Thornton Tomasetti. Longtime structural engineer, started at TT back in 1995. So it's really exciting for me because I was telling some people in the room that when I started in 1995, we didn't have computers. We had a couple of computers sitting in the corner that we had to run to do our analysis. So we've come a long way, I would say, since then in the last 25 or 26 years or so. And presenting with me is Sergey Pigash, who's going to give an intro.
Hi, my name is Sergey. Thanks everyone for being here. I'm a developer at Core Studio, and I actually have a background in architecture, and then by virtue of exorcism by fire, I kind of moved on to software development. And yeah, I write Cortex, which is one of the many things we'll mention today. So.
Cool, thanks, Sergey. And let's see how this works here. There you go. All right, let me know if the sound is it coming through, actually? Okay, I gotta get closer. Okay, so I'm being ambidextrous here because the screen is controlled by one computer and I'm using my notes here on my other computer. So if I start speaking incoherently, just let me know. So a little bit about Core Studio. Started out as Core Studio. It sort of branched out into other initiatives in the firm. Originally stood for core computation plus research, and it's become more of an ecosystem in the firm. There's the Core Studio, which I'll introduce at least the faces and the names of the people that are in the group. But also, we run the firm-wide R&D program where we allocate quite a bit of money for R&D projects that anybody in the firm can put forth an idea and get funded for. And then we, when we started to research machine learning and AI back in 2015, we realized how powerful it could be for our industry. So we started Core.ai. And back in 2018, I believe we officially did that. This is the team, Core Studio team. And the names in red are the people that work regularly on machine learning projects throughout the firm. And, we have some real experts, some in the room here who have data science master's degrees and PhDs. So it's an interesting science because it's not something that, the general structural engineers or AEC are familiar with. And so I think the process that we've taken over the years is to learn what is possible and then start incrementally applying those principles to our data sets. So if you don't know, you should know that AI is pretty much everywhere. Anything that you do, and I will say a lot of these firms would not exist if it wasn't for machine learning and AI. So it's pretty much done on a daily basis. Anytime you open your phone, something is happening in AI machine learning, and it's way more advanced than what we're doing. So we're sort of starting baby steps with what can be done. So hopefully we'll show some of that. I grew up in the 70s, so I used to watch this show called Lost in Space, and there was a man inside of in a suit waving his arms around. It was called Lost in Space. But that is like real today. There are robots that can do very advanced things. And so even in the 80s, there was a Terminator that was recognizing certain things visually about people and various aspects of the environment. And that is real today too. That was fake back then. So I think the speed of the technology is coming really fast. And this is an example. Tesla is using computer vision 100% to self-drive cars. Now, in my opinion, it's probably like a 16-year-old at this point, but that's pretty amazing, actually, what it can do just by using computer vision and monster data sets. And well, I'll get to it later about why it's potentially even harder in our industry than what they're doing. So in a relative scale, where we are in AEC with machine learning, we're kind of at the beginning of the journey of what can be done in AI and machine learning. It's being done ridiculously in the tech sector, but I would say on our business, we're just starting. But I think just like the tech sector, the advancements will come fast, fast and furious. And so the first question people ask me about machine learning and AI is, why should we do it? We have very smart engineers and architects in our office. We have the best and brightest. Why should we do this? And why automate in general? And I mentioned I started in 1995, and I will say what occurs today on projects is way, way more complex than what I had to do back in the day. The speed of projects, the amount of information that we have to process and produce, and the speed of project, the changes that occur just happens way faster. You can't make changes, and some people may not know what I'm talking about, but we used to get Mylars for design. So you can't make changes in Mylar, right? You got to erase the thing. So manually. So it's not something, now you can just push a couple buttons. I guarantee every single Revit model is different on, by the minute, basically. So we have to be able to keep up with all of those things. Big picture wise, again, this is a why we need to automate in general. Scope creep and feed challenges. So I tell people 15 years ago, or even 10 years ago, if I was doing a concrete residential building in New York City of 20 stories, it would be concrete. You wouldn't even, there was no questions. It was concrete building, you would move on. Today, it could be concrete, it could be steel, it could be timber, it could be a hybrid. And so our fees haven't changed. We have to do all those options to get costed. So we're having 3 to 4 times as much work to do in the same amount of fee, relatively. Schedules are ridiculously fast now. There's a lot of challenges there with schedules. And I'm sure, as you all know, in this market, talent is very short these days. I think in our industry, it's like a 3% unemployment rate, which is ridiculously low, meaning we don't have the same pick of people that we typically get, which is a challenge. So it's going to take people longer to get experienced. There's a lot of movement in the industry, a lot of people moving to different offices or different careers. So that's a challenge for an industry that relies on intelligence and experience to produce their work. And I will also say that the software tools that are available, and I'm not going to pick on anybody, but they're really not made for what we do on a daily basis, particularly in the early design phases. A lot of the software that is out there is really made for construction documents. But as you all know, construction documents is only about, if you go by fees, 40 to 50% of your fee and the time associated with that. So the other 50% is, or let's say 20 to 50% is doing other things, is, schematic design, design changes, ideation, other things that are not related to the software that is produced commercially. So we need to create tools that will be able to handle those types of pressures that we have. And the other thing is, a lot of people in this room, the tools are not made for high-end engineering and architecture. They are made for the masses. And so I tell people, like, if you want to win a Formula One race, we will not win it with a stock Ferrari. It's going to have to be a very customized car. So that's kind of where we are in our space. And also, I would say, again, something that was not even an issue 10 years ago or 5 years ago even, is the whole climate change decarbonization issue, which, life cycle analysis and things like that didn't exist, but clients are asking us to do this on a daily basis, and we have to respond to that. So this is a little graph that I put together that also explains why we need tools that can rapidly sort of prototype designs, iterate through options, but also include, I will say, the intelligence, the historic intelligence, institutional intelligence of very senior people. And so, I show the SD, DD, CD, and our tools are very good. The commercial tools are very good for CDs, but for the other phases, they're not very good. And so in the early phase of design, you really need some either software or a person, but that's the problem. You're not going to get a person with 30 years experience to be on every single project at all points in the time. So how do you embed the intelligence of someone with 20 to 30 years experience in an app that they can access, such that a young engineer or a project manager will have the answer at their fingertips during a project at those phases? Because we don't want to do full design, schematic design, which is something that a young engineer will start to do, which is a mistake, actually. And if you think about it, and I've been thinking about this quite a bit, because we didn't have the tools back when I started. So we had to basically ask our project manager, or they would tell us what to do and what they expected from us. It's very difficult these days, a lot of times, because the project managers and people with 30 years experience actually don't know how to use the tools that the engineers are using. So we can be, I say this a little bit facetiously, but engineers can become, if they don't do it right, they start becoming technicians, and they're not thinking about the engineering principles and sort of moving towards their target, but more treating a project like a research project, which is very time consuming and costly. So when we started this back in 2015, I have to give credit to Dan Reynolds, who was in our group at the time. And I'll show you what we did here, but we wrote this paper on machine learning with his wife, who was a PhD in machine learning and data science, so that was helpful. But we published this paper about calculating the embodied energy of a building, of any building massing. And again, this is something that we were doing a long time ago. And I also presented this at the AAA convention in 2015, this particular tool. So the question was, how do I take any building massing, any base spacing, building height, sort of the typical metrics, and calculate, have an answer about the embodied energy of that particular building, and different materials as well. So we started to look at this, and you can see here that if we actually went through those old options, there was 10 million possible combinations of solutions. And it would take, if every analysis took 5 minutes, it would take 95 years to actually produce all the data sets for this particular problem. So we knew that wasn't feasible. So we started to look into machine learning back then. And we were able to produce, and again, it took us like, just to produce the 5,000 samples, that took us like at least a month of running analysis to get the 5,000 samples. But we were able to get within some reasonable error, an answer within, a couple hours of training that model. So that sort of like really, set off a light bulb within what we could do, because in those early phases of design, you're really interested in having enough information to give to your client or to your architect so that they can, with some level of clarity and accuracy, make a decision to move on to the next phase, and not potentially having to, only do 3 options when, they decide to go with some option that has nothing to do with the 3 options, and that 4th option is a very bad option, and you have to start over again. So, so then we started to like really dive into machine learning and AI at that particular time. So just a quick overview of what it is actually. So this is some things that I pulled out of off the internet or whatever, but I think it's computer science that can create an intelligent machine that work and act like humans, react like humans. And I think we're not there yet, but I think even if it's the narrow AI, that's kind of what we're focusing on. And there's different types of machine learning within, I should say, there's types of different intelligence within that concept. We're focusing on machine learning and some deep learning. We're not recreating a human necessarily, but we are sort of trying to recreate certain human processes, repetitive processes, in the things that we're trying to do. There's a lot of different types of machine learning. Most of the things that we are doing are supervised learning, but there's others that are not. Unsupervised learning, which we will talk about a little bit later. And this is a good slide that I'd like to explain to structural engineers particularly. So I've taken a couple AI courses, and this is the one that sort of stuck to me as it started to sort of like make sense to me. So we're all familiar with the equation of a line, y equals mx plus b. The y being the dependent variable, the sort of answer we're trying to find, x being the variable that sort of creates that line, and m equals the slope, right? The cool thing about machine learning is the variables that are possible are infinite. So it's not like x, it's xi to xn. And basically it's fitting a curve, a line, through a series of data points. So there is going to be an error there between those data points, as you can see. But again, in those early phases of design, if we're close enough and we have some confidence and the data is good, then we should be able to rely on it. That is the sort of interesting point, and it can include multiple variables. And I'll get to that more with like some of the machine learning projects that we worked on. That was sort of the thing that sort of clicked for me in terms of like thinking of my brain, like what machine learning actually is. It's basically you creating or using data sets and fitting a curve, and then being able to, with multiple input variables, find an answer immediately without doing any calculations. So I think this was also interesting too. So Google did this years ago. AlphaGo was something that was trained by humans to play Go. It's a complicated game. And AlphaGo, after some time of being trained, beat the world's best Go players back in 2016, 17. A little time after that, something called AlphaZero trained itself. So it didn't rely on humans, they train itself how to play Go. That version beat AlphaGo 100 games to nothing. So that was an example of like what's possible. We, because of the way that we've learned over the years, do things in a very specific sort of serialized way. And machine learning does not care. about serialization because it can do things in parallel. It can do things that you're not thinking about from a human standpoint or a time standpoint. So I think that's a very interesting fact. We're not there yet, but I think there is going to be within machine learning and AI that can be done way better than what an engineer could do. So this is I think a good explanation or description of what machine learning is. So we're training an algorithm. It's not actually being programmed per se. I am behind down here. So so let's go to how these things are generated. So I would say these are the key points of what is, or the key topics of what is needed. You need data, you need expertise, and of course you need data science experience. Every firm has the domain expertise. Data, not every firm has. That's the hardest part, I would say, in what we've been doing. And of course, data science is not easy either, because it's not something that is typically trained in the traditional structural engineering curriculum, which is why most of the people that we have retained for our work either have specific PhD work in data science or master's degrees for that. So this is sort of our process in terms of like figuring out what applications and what models to create. So every engineer, and this is not easy either, engineer has a different process to getting to an answer. And so the first thing that we do is find out what certain processes are for early design, what processes for detailed design. And we're kind of focused on the early design. Again, especially in the beginning, there is going to be some error, again, hopefully within certain tolerance of machine learning model. But as long as we can get some confidence that those errors are minimized, then we can get the engineers to use it. So that's the first thing that we do. The next thing that we've done over many, many years is to encode AISC, NDS, and ACI code-based algorithms in our sort of what we call course structure, which is our programming library that we've written all the equations in code. So what that enables us to do is create huge data sets using the code base, which is again, even that itself and how to do that is not easy, but we've done that over many years, and so we have that. So this is an app that we created started in like 6 or 7 years ago. That is something that I used to do manually, which is bay design. And this is we created a web app that calculates steel beam framing, including strength and vibration calculations, sort of on the fly, completely parametrically. It is way better than any commercial software that you can get, and it is CD level sort of analysis. So in RAM, you got to do a strength design, and you got to do some separate vibration design, and it's half right. And you got to do your own spreadsheets, whatever, and then you got to manually change all the members. This does it automatically, and so the nice thing about this, and it also does sensitive vibration. The beautiful thing about this is that now we know we have a code base that we can rely on. We know it's going to be right. So we'll get to that a little later. So to create the machine learning models, we have a library called core.learn, which is our machine learning model database. So again, we've taken the sort of the data that we synthetically create, as well as the data that we have from experience, as well as we sort of cull certain input data, because we know that it's not, again, just from experience, you can do it, you can actually calculate these things, but like that don't have that much an effect on an answer. And so, and then the goal of this is to, once we create a model, we create an API for this, which is application program interface. So we can use that designer, let's call it for a column designer, for beam design in any application, sort of on the fly. So 2021, Omid, who's a PhD from University of Buffalo, is working on machine learning on his PhD. And we decided to sort of up the skill in terms of complexity of what we can do. So we did these concentric braced frames, chevrons, and trained a model for the concentric braced frames for 1 to 15 stories. And the reason why we did 1 to 15 stories is because it's a lot of data to do this. So we're doing this in steps. And so brace frames are, required for steel tall buildings. They're time consuming to do. And so what we did was this video here shows the red being the machine learning predictions and the blue being the synthetic data set generation of a scripted calculation. So you can see the correlation is pretty close. And again, there's always going to be some error with some machine learning, but if we're close enough, we can trust it. And I will show where we are with that now. So a couple of case studies, and I'll go through these fairly fast here. So the first one was how to we use sort of what we had built upon previously in 2015, and we created an app called Asterisk in 2018. And yes, it does take a long time. So this app is able to calculate a building structural design, beams, columns, slabs, cores, brace frames for a steel or concrete building in under a minute. So you will see this. And it was very difficult, but we made some mistakes and we learned from this. And I'll go over that as well. But it was a web app, or it is a web app, it still works. And so this is kind of how it works here. It works, the massing comes from a CAD client, we use Rhino. And then there's a web client that it talks to. And then we have what we're calling a geometry service. So it's a pre-processing layer that sort of slices and dices the model up into a wireframe. So, beams and columns and slabs, et cetera. And then we have the machine learning sort of layer where those pre-processing layers goes into. Those are inputs for the machine learning models, and then there's a prediction. And the prediction is shown, is uploaded to the web or phone or whatever. So there is quite a bit of intelligence in there, particularly in both machine learning, but also the pre-processing layer. And you will see in this picture here that the geometry service, as we call it, is pretty smart. So it can take any massing, dice and slice it into beams, columns, girders, and it actually understands also corner bays versus exterior bays versus interior bays, which is very important for those structural engineers to know about beam design vibrations. So it's ridiculously fast, especially compared to human, because the human would try to take 3 weeks for each one of these iterations. I think one of the things that you learn, or you need to learn from machine learning analysis, is that qualitative design and what we call optioneering is something that is the sort of goal of these apps. Which engineers are not used to. We're used to producing answers for 2 or 3 options. That's the answer. But if you can do 100 options, then or 20 or whatever the number is, then you can start to see sort of optimizations, but also your client can see sort of where the sweet spot is of their particular design is. And I think that has sort of now finally coming into play. So this is a little video. Again, 2018, we built this. This is a massing for Tower C, which, or 10 Hudson Yards, which, what's it? Oops. That's a bummer. Playing on my screen. Okay. Well, what's that? Yeah, no. It's fine.
If you use your imagination.
Use your imagination. The app, and we can upload this at some point. But what the app is doing is, so this is doing multiple options for this particular tower, and we can do, again, change the base spacing, change the materials, change steel versus concrete, predicting slabs, columns, et cetera, all of that. In under a minute. So the metrics that we are calculating are in this app are total area, which is pretty straightforward, total weight, which comes from the predictions of all this of the structure, embodied energy. Again, back in 2018, no one was talking about embodied carbon, so we went embodied energy, and all the associated loads associated with what that's predicting. So to show that it's actually real, what we did, this app called testfit.io, which is commercial software doing sort of generative planning for residential buildings, is using our machine learning model for their column predictions. So, I think it's really interesting because the sort of tech sector are really looking for these things, this type of analysis. So it's doing the sizing sort of on the fly, which I think is really interesting. So some of the pros and cons of the app, and this was important for us because we, with any R&D, you need to either fail fast, as you've heard, or at a minimum learn the mistakes that you made and how you can improve on those things. So I would say back in 2018, machine learning and automated design was probably too much too fast for most of the industry and for even Thornton Tomasetti or anywhere, I should say. Now people are dying for it, but back then it was not trusted. It's very black box, so you didn't know where the data came from necessarily, and predictions were close, but like no one's going to go through 1,000 elements and check every single one. The other thing, asterisk, was for a single building typology, so a tall building with a central core. Data sets were code based, so the results are actually too low. There's not a building on the planet that is designed with every element with the design capacity ratio of like 0.99. Forget it. It's like most buildings are designed 20 to 30% over, and from code base for drift purposes, for other purposes, reasons, I should say. So the results when total results always ended up being a little bit too low. So that's where we need to sort of layer in the experience part to make sure that, or at least have a way to increase those values so that it's more real. The other thing was the ML models that were in the app were locked. So it was not like we can swap out when new data was available. They're sort of locked in there and we couldn't get it out. Pros of this was that it's first of its kind. It still is. There's still nothing else out there like that. The metrics that we were predicting, weight, cost, embodied net carbon, et cetera, is exactly what you want today's projects. We learned a ton, and as I mentioned, that sort of embedded intelligence in an app, in an API, is very sort of desired today. So I'll talk a little bit about T2D2, which is currently started out as a research project in our core lab entity back in 2017, I think. And by the summer, just one summer, we were able to predict certain cracks using computer vision with an intern, very smart intern, and Badra Hirier, who's now CEO of T2D2. And so that proved out that this is extremely powerful because, again, we're using the experience and the data sets from Thornton Tomasetti because we have a lot of data for that type of work. And so the pictures that you see here is what was done in that summer. So we were able to spin up an Android app that was able to predict within some level of accuracy certain types of damage just using computer vision. It's come way farther than that. And so for those of you who are not familiar with computer vision, basically, when a human sees a cat, say, we recognize all the features of that particular cat. A computer only sees numbers for that. But if you feed that machine learning algorithm enough data, sooner or later it figures it out. And so so we were using cracks instead of cats, right? Or balls. It's a very complex app. So there's not just a singular computer vision app that is detecting damage. It's actually checking whether it's structural or non-structural. There's a machine learning model that's sort of knows how far and close you are to a particular, let's say, facade. It knows the types of materials, so steel, concrete, brick, terracotta, stucco. It knows, it has enough data so that it knows what type of material it is. And then of course it knows what damages are it's seeing. And if you think about this, this is exactly what a human does, right? The first thing we think about, we zoom towards, we forget about it because it comes naturally, is we automatically know what the material is, or we automatically know proximity. We automatically know whether it's structural or non-structural. But a machine is dumb unless you train it to be smart. So it's sort of stitching all those things together. But the beauty of this is it can do it at enormous scale as compared to a person. So again, it's a complex app. It has a way to, when it does predict the wrong thing or something that is not a crack and it needs to be something else, it does have a way to sort of manually, the human can correct it, like a child essentially. And then all of a sudden it learns, it gets smarter and smarter along the way. So this is a quick video doing a stucco building in Florida. And you can capture these damages just using a drone. And each one of those little boxes is being captured and categorized, classified, and put in a database so that it can be retrieved later and quantified. So again, what it's doing there is is probably weeks of time for a person to do. So that's sort of the power of what machine learning could do in a project. I'm going to go through this quickly, but this was also a little hack project that we worked on. This is, if you're not familiar with Construe, we created a app called Construe, which is a data interoperability platform mainly for structural engineers that allows you to, it's a centralized database model where it's sort of, I refer to as like Google Translate for BIM. And it talks to all these different platforms seamlessly, bidirectionally. But so the question is, and this is like a $1 million question, right? Can you use BIM models for machine learning or to train models? Because it is good data. We have a lot of it. So we sort of decided to take this building, just one building. We were the engineer for the West 57, VIA West 57 building up in West 57th Street, New York City with Bjarke Ingels Group. And so what I wanted to do was just predict a column size. And so for that particular building, use machine learning. And so Construe allows you to export all of the BIM data within the model into an Excel spreadsheet, which is easy for me. That's the level of tech that I can handle. And I was able to parse each one of those columns into a data set with the only prediction, the only sort of input was two things, was the size of the column and the number of columns above. And if you think about it, and most experienced engineers can tell you with some reasonable accuracy without doing a single calculation what a column size should be for a 40-story building. No calculations at all. And so the question is can you put that into code, into a machine learning model? Yeah, and I'm going to say the answer is yes. So anyway, I was able to sort of create unique IDs for each one of these columns, calculate, from the model, like what was the number of columns above, the levels above, and this is just a picture of the model colored by column size, and even just looking at the column sizes and the colors, you can start to see some patterns, right? All the top columns are all the same size. Why? Because they have very little load. And so they're the minimum column size. The ones at the bottom within the mass, with the very big massing, are way bigger and different colors. So we probably can use unsupervised learning to calculate this as well, but we used supervised learning. Anyway, not to go into the tech too much, but we were able to train a model with just that data and be able to calculate within some reasonable accuracy what a column size is for a residential building of that type. So that was a good test. But I will say, the types of things that we do are typically very difficult. So this is a model of a little picture of what a Tesla car is. So billions and billions of data points, some pre-processing, a lot of machine learning models, but there's only three things that they have to control: the brake pedal, the acceleration pedal, the steering wheel. Our problem is much harder. So we get multiple inputs from an architect or owner, and we have to create very bespoke applications at a particular point in time, do some pre-processing, feed it through our algorithm or our process, and then we have an output that gives back to the architect that they can then use for the next iteration. So the challenge is that our process is circular. And so we need these apps to sort of process information really quickly. And so Sergey is going to talk about something called Cortex that we've been working on for a while that handles that process, which is data, machine learning model creation, as well as the ability to create a very bespoke application using APIs, REST APIs, which is, I think, the key is that our processes are very bespoke, and therefore we need applications that are very much like a recipe. It's not going to be the same recipe every single time, depending on the point in process. The accuracy of those models are going to be different for every different point in time, and so we need a very simple way of allowing machine learning models to end up in applications. So Sergey is going to talk about this.
Cool. Thanks, Rob. Yeah, so Cortex. So that's a platform that we've been working on for a while. And the main motivation for us undertaking this adventure kind of comes from actually the Asterisk days, because I had the pleasure of assisting Dan Reynolds and the team back in the day as an intern. Leland remembers, he was there, on building that application. And one thing to mention about machine learning models in general is that, despite what TV might suggest, they're not magic, right? Like right now we're dealing with machine learning models that are kind of those narrow intelligence, very narrow task focused estimators, right? So they're very, very good, or they can be very, very good in very narrowly specified tasks. And when it comes to using machine learning for projects related to such fields as structural engineering or architecture, the space of the inputs that you have to deal with and the possibilities for solving the same problem multiple ways is exponentially larger. So you end up with a great number of models which basically allow you to break up a very complex problem into very compartmentalized steps and then solve it in this kind of distributed way. But what this means in practice is that you end up with a bunch of different machine learning models and a bunch of different data sets. And it's very difficult to manage that chaos, especially because, even in the industry, people with the data science background, for instance, come from more of an academic background, which has more of a kind of like an experimental research spirit, but they might not necessarily be familiar with the same kind of continuous integration, code versioning patterns that are used in, let's say, software development as a field. On the other hand, you have software developers that are very familiar with those workflows, that are very familiar with kind of building systems for testing code and version control and those sorts of things, but they have no idea what data science is or does, and the communication between the two is quite difficult. So that's why we decided to build Cortex as a platform that, on the one hand, will get you from a data set on your machine to a web API that can be used for building an application in record time, but on the other hand, also allows developers and machine learning experts, data scientists, work together in some sort of a coherent pattern. And then once you have Cortex as kind of this hub where you can log and track your machine learning models and kind of keep everything neatly in order, it can then enable different other applications that are built on top of it, and to just use those machine learning models as API endpoints. You really don't need to know what happens behind the scenes. You're basically, for those of you who don't know, API is an application programming interface. Freudian slip there. And it's essentially how machines talk to other machines, right? Us people, we use graphical user interfaces or human interfaces. Machines talk to each other through APIs. And you don't need to know how the API or the service you're calling solve the problem, whether it uses machine learning, where it uses kind of traditional algorithm-based computing. You're just getting an answer to your question, and that's all you need to worry about. So this is what Cortex looks like. We have what we call experiments. We're kind of stealing nomenclature from what's currently standard in the data science field. So within each experiment, you're able to log a number of runs. So we actually wrote our own Python library, Cortex Python library, that allows you to take a machine learning model from a number of popular libraries with support: PyTorch, XGBoost, scikit-learn, and TensorFlow Keras. And you can just call a log model function, and it's going to take your trained model and it's going to serialize it to disk and push it to the cloud alongside all of the metadata, alongside all of the information about who developed this model, who trained it, what data set it was trained on, what are the hyperparameters, what are the metrics, and so on and so forth. And then we're also able to deploy those machine learning models as APIs. And we also have a data store. So you keep your machine learning models and data sets in the same place. You're no longer searching for CSV spreadsheets across different GitHub repos and folders on your hard drive. And this is just a view of, you're actually able to query those data sets regardless of the size through the web app. And so by using Cortex and kind of by bringing the data and the machine learning models and the ability to quickly, press a button and create a web API that then the development team can use, we hope to, bring some structure to this chaos.
Yeah. So I think the key aspect is that we can sort of, again, as I mentioned, sort of like as a recipe, pull down. If we're doing a timber building one day, we pull down the timber applications. We're doing steel building, we can pull down the steel building machine learning models, et cetera. So which we'll show a little bit of that. So this is recent, very recent, like last night when I was working doing this last night. But no, there's some stuff it's been going on for a long time. But I will say the sort of the time that we're taking from ideation to machine learning model is significantly shorter. Asterisk was like years, to be honest. Now we're talking weeks. So that's the difference in how we're getting there. These are the machine learning models that we currently have. There's a lot, and I would say the beginning of this year there was none, so we had to retrain all the models. And so if you look at this list, this is probably 80% of what we do as structural engineers, particularly in the linear design process. So we're getting there. So this is very recent. This is a timber column map using machine learning that has all the various species, and that you are able to calculate a timber column size on the fly. This is using Cortex, actually, using our swarm map, which is now going to be, we're going to start using something called Shapedriver, which uses swarm technology, which is basically Rhino compute in the cloud with a beautiful viewer. Their viewer was way better than ours, and an interface, graphical interface with a Grasshopper and machine learning or other backend that you can call. So, you can add, tell me some engineer that can design columns this fast, on the fly. And so this is the sort of power of machine learning, where you are embedding answers in an algorithm. This is Chevron concentric brace frame that we are designing members on the fly. Each one of these probably takes the best engineer 4 to 8 hours, and then we can compute this in probably under 30 seconds each version. So when you're doing a tall building design, what is the first thing you have to do is calculate the lateral system. It takes a long time, but we're hoping to do this in hours versus days, or weeks versus months, let's just say. This is a concrete column designer, which we had for a long time. Again, this is using machine learning. It's ripping fast. This is real time calculation. So we actually have controls of the reinforcement ratio as well. In this case, we kept reinforcing ratio constant, but you can filter that as well. We're actually using k-means clustering to sort of cluster the number of column types on a particular column stack. But this just demonstrates what the sort of power is of machine learning and the speed that's there. This is the most recent version of our Bay design. And as I mentioned Skipper in the beginning of that was a trusted data set. So we were using Skipper data set, Bay design. And Skipper looks very simple, but it's actually very, very complex. It actually designs 8 different bay types, depending on corner, location, number of bays in the X and Y direction, if all the engineers, you know what I'm referring to. And this one's calculating office loading type vibration criteria. And we sort of held certain things constant, but this is just demonstrates what can be done. So this is doing a vibration design and strength design all at the same time on the fly. And you can see how it sort of looks from a color standpoint. So it's starting to look very, very correct. And this is like, again, many, many times faster than what a person could do, or any other software. This is an example of a project that we're working on, doing a steel building, concrete building, and a timber building all at the same time, using both machine learning and also some other just basically rule-based calculations. We are using the asterisk 1 machine learning model for the steel and the concrete building, calculating embodied carbon as well. At the same time, we're using an algorithm to calculate the foundation type. And it's a very interesting study. There are things that we discovered in doing this analysis, because timber is typically like half the weight of concrete or even less. And that is very interesting. And you can see the columns change in size. Timber column sizes get very, very large for a tall building. So that's also like a design aesthetic constraint, I would say. But this is what's possible. And this is what we want to do in those early design phases to get the designers and the architects sort of able to make the decisions really quickly without having to sort of go back and figure something out. So this is just a case study. I'm going to flip through this pretty quickly because we're running out of time, but this original presentation was given at the NASCC Steel Conference in Denver. And so we decided to create, again, using our encoded core structure library, where we have a bunch of tools doing Tekla automations and trusted, sort of tools. And again, is this going to work? Let's see. Put my mouse. Let me see. Yeah, go ahead. I can't even see them.
In a moment. Oh, you have to actually click the button.
Yeah, there you go. Okay, so this is 30 Hudson Yards, showing a floor in Tekla. We have the shears embedded in the model, and what it is doing is it's populating all the shear connections on the fly, using our automation tool that we've created over the years. And so again, this is fabrication ready design intelligence. And again, each one of these connections takes an engineer, the best Tekla detailers, about 10 minutes to do. So we're doing, 230 plus connections in, under a minute. So that's the sort of power of automation. And so what we decided to do is use that data set to calculate connection weights for a particular building. Nope. Should be this one, right? Is it moving? Okay, well, so unfortunately, OneDrive is not my favorite software, but basically, again, we can provide these slides. What it is doing is something that engineers sort of make a way their hand guess at is the weight of connections for a project, because we have to assume some weight which equals cost in a project. What this does is calculates for every single connection in the building, typical beam spans and girders, the differential between 3/4 inch A325s and 1 inch A490s, the weight of each of the connections in totality. Now, an engineer could do it, but it would take them weeks to do for their entire building. We can do it on the fly. And this is to demonstrate what's possible. So we're predicting the number of bolts for each connection based on the shear, post-processing the weights of all those connections because that we have in Tekla, and then you can calculate the total weight. This is just a demo floor plan that we're showing. And it's something that I think is, again, one of those things where like we can do it as in our process, but we're not really getting paid to do that. So we don't do it. We kind of make a guess, and machine learning could do that sort of really quickly. So there isn't an ROI, obviously, for all of this stuff, but it's hard. Machine learning, we've been doing this for years now. There's a lot to do and learn about machine learning creation. It takes a lot of resources that we found. But again, we think that there is an ROI, return on investment, significant return on investment if we do this. And so just an example, this is a typical beam data set potential. So this is some things that I've put out there: beam span, metal deck height, concrete topping, concrete strength, all the things that we our inputs in a composite beam, construction dead load, SDL, live load. Just by doing this small little subset of inputs, this is only a subset of inputs, you could end up with 66 billion data points very easily. That's why this is really hard. You blow up your any computer that you have. So we have to use our experience and also use the data science expertise to get close enough without having to do this. So what do I think in summary? I think 30 to 40% of what we do can be automated. And I don't mean 30 to 40% of a certain process. I mean 30 to 40% of a total project. The productivity is I think is huge. I also think AI machine learning could be used for checking QA/QC, just to find those anomalies or those potential blunders or errors that are made by engineers. They can find trends in large data sets, whether it be engineering or financial, that can assist project managers and engineers to make decisions faster, which is basically what we do as engineers. We make decisions. I think finally, this is a huge point, is it would be incredible if we can capture domain knowledge in an application, because the sort of strength of any company is its people. But when those people leave the company, you never long have certain expertise that you would love to capture, in an application, say. And so, my little fancy stuff here, but basically, this is what I'm referring to. So, how do you capture intelligence of a firm into an application? And I think machine learning and AI is one of those. Is the application that can do that. That's it. So
Great, thanks, Rob. I have this cube microphone. Does anyone have any questions? You can toss it around.
Oh my God, it's a cube. Wonderful presentation. I know that Core's in an R&D group, so you're abdicated from having to have a specific or serious answer to this question, but what exactly is the value proposition of the kind of AI that you're showing here?
Well, the first one is just going to be speed. It's just going to be speed and productivity. I think that's the main thing, and response time. Engineers are paid to respond, and the quicker we can respond, the more informative we can give, be for the designer and for the clients, and that'll get us there. The other issue is, I kind of touched on this, is that do engineers really need to have a master's degree and spend their time for the first 5 years of their career clicking buttons? Not really thinking, right? Not to say that there isn't value in clicking a lot of buttons and learning along the way, but it's a big waste of time. I spent 5 to 10 years clicking a lot of buttons. We don't have the time. We don't have that time frame anymore. We just don't. We need to have engineers quickly ramp up to get to, because like I said, there's a lot of churn in the industry these days. So I think that's the other value proposition.
Yeah, I guess I want to push a little bit harder on that. So if they weren't clicking buttons, then what? And also, does that inevitably result in just a firm being able to deliver more projects, or what?
So what we're thinking, right, is that if you can automate certain, again, mostly the early stages of the project, the engineers can focus on the more intelligent, creative parts of a design. Again, the machine, like I said, these machine learning models are dumb in a way. They're only trained on what data that we create. Or obviously they can get smarter, but in our field, I think the uniqueness of an engineer and an architect is their ability to be creative. And I think that's what we want to have the engineers spend their time on, the master's degrees and the PhDs, as opposed to clicking buttons in an ETABS model to make sure that it runs correctly. We need to do that because we need to develop a code-based design, permit-approved, safe building. But that's, in our field, it's like 40 to 45% of the design is that. The rest of it, I think, could be.
I see. So the unbridled creativity would manifest in the built world, and it would be a better place for all of us.
and we'd have more completeness, I think, in our designs as well. So, if anyone says that they're 100% complete at 100% CDs, they're probably lying, right? We can get more complete, more thorough with what we do if we had that time to do it.
Great.
Hi, great presentation. Thanks for showing it.
Is that working?
I think so, yeah. I have two quick questions. So the first one would be, if you guys are spending 40 to 50% less time doing the work, does that change what your billable hours are or what your billable structure is for the client? Or is that cost savings for you or for the client or for both? Or are you still charging the same amount? I'm just kind of curious in that realm, because if you guys are doing more efficiently and you're billing less hours, then you're bringing less revenue for your company, no? Or?
That's a great question. I would say both. I would say both. Obviously, we're a business, so we want to make more money. But on the other hand, particularly Thornton Tomasetti, our fees tend to be higher than most firms. We're a larger firm than most firms. Overheads are higher. Therefore, the same hour that we spend costs us more than the hour that another firm spends.
Mm-hmm.
So we need to be more efficient by definition, just to make the same amount of money. So it's both.
Sure.
It's both.
Great. And then the second question I have is with regards to office adaptation of this process. Is it? I mean, you have the core team, which is great and really well known within the industry. But are there team champions, or are there people teams throughout the office that can utilize this, or does everybody use it, or what is kind of the adoption rate? And then how do you also do that internal training to upskill people to be able to develop this?
That's a very good question, but we have started that. So we have, as part of Core Studio, it's not just development, it's also a modeling team that supports projects daily. And they are able to sort of hook into all of our tools to use on projects. So in some cases, once these project managers get comfortable with the answers, then it's like, you'd be stupid not to use it, to be honest. And so we're in that phase of like getting project managers comfortable with using these tools early on in projects because it saves time, saves money, and it gets answers really fast. The other question about sort of broadly like upskilling and training people is that we've actually given with the Northeast with the RU Institute, which is part of Northeastern University, created a series of classes for engineers and very senior people in the office to get familiar with AI and machine learning, get comfortable with it. So it's a process. It's not like one day machine learning model is going to take over. It's going to be like you need to get people familiar with it, understand it, comfortable with the results, and then hopefully drive the next applications. Right now, we're sort of, we've been doing this for a long time in core, so we're familiar with it. But I think the industry and the larger firm is starting to get more comfortable with it as well.
Sure. And I guess maybe one more question.
Sure.
So it's fairly clear that TT seems, or at least leadership seems fairly supportive of all the efforts that Core have been doing for many years, and particularly with the work that you've been doing. Can you explain maybe sort of what the strategy was, or what the process of gaining that support from leadership for going down these endeavors, even like back in 2015, where no one even knew what AI stood for, besides Adobe Illustrator? Like, like what was that process like, and how would you suggest other firms within the AC industry kind of pursue that with their leadership to try to push new initiatives like this?
That's a great question, and I will say TT is at a somewhat of a sweet spot in terms of our size that allows us to have some discretionary funding to push some of these ideas through. But I will say we've always treated Core Studio in the firm as a startup within Thornton Tomasetti. So we need to demonstrate return on investment on everything that we do. In 2015, I didn't tell anybody that we were doing machine learning and AI research, to be honest. They didn't know what it was taught. I would talk about it anyway. So it was like a yes. Sometimes you don't want to ask the question because you'll get a no, right? But we were still creating apps like Skipper. We were doing a lot of computational modeling on projects. The ROI was always there. We were creating Construe, et cetera. So we've always left some money for, I would say, transformational research. And I think you need to in a firm. Again, depending on, it's a small amount. It's a small relative to everything else that you're doing in the firm. But if you're not trying to hit those really big ones, I think, I'm not to say it's not valuable, but it was something that we saw in our group that was could change the industry. And I think the technology has come a long way. I mean, we couldn't do what we did today 5 years ago, even if we knew about it. Technology is going so fast. So that's kind of the answer. I didn't tell anybody in the beginning, but I had that discretionary. Yeah.
Great, thanks. Any other questions? Sure. Maybe one last question.
This thing's cool. Yeah. So every architecture firm, every structural engineering firm, we're all sitting on a massive pool of data. With this process, Thornton Tomasetti may have been the first firm to actually organize the data and store it in a retrievable way. Do you think that this data set has opportunity to be monetized outside of the construction and engineering space? If so, what do you think those opportunities look like?
Well, I will say, majority of the data that we've used is when it comes to the structural engineering apps, not T2D. T2D2 is pictures and stuff that we've had over the many years, terabytes of information. Mm-hmm. But for the structural engineering apps, we've what we call synthetically generated those apps at that data set. So again, we're using our what we call our core structure encoded library of design algorithms to create the data sets. So we've encoded, composite beams, steel columns, concrete columns, all those things. And so we're able to create millions of data points, not that we need millions, but we could if we wanted to use as data sets. In terms of what the information that other engineers or any architects have, the hard part of that is mining it out, right? And so the reason why I experimented with Construe is a database. It is not a binary file. It's not like Revit, where you try to open a Revit 2015 file. It's like you lose half the data. So we can create a CSV from a BIM model. That's the reason why, like, in my mind, I'm thinking, in order for us to extract data, you either need to create a way to read drawings automatically, right? It's hard to do. Half of the information is not there in the drawings, or mine your BIM models. And there's probably other ways of doing it. We use Construe in our case. So I think firms need to start thinking about that. Like, the traditional, saving PDFs is okay, but to mine the data out of a single project probably takes someone days, right? And that may not be sort of financially feasible. So I will say we have looked into automatically trying to do it using PDFs and image files using machine learning and other applications, but that's it's not easy. So the answer to your question is there's a lot of value, a ton of value in your project data. The hard part about it today is to mine it out. And you have to be careful. Like I said, 4 or 5 years, 6 years, your Revit files will be dead, completely not usable unless you're, save your Windows 10. And, again, most of our Revit files are from 2008 or 10. Or forget it. They're not usable anymore. So you need a way to extract the data as opposed to keeping it in a file, binary file.
Great, thank you. Great presentation, by the way.
Thank you.
All right, if that's it, we'll say one last thank you to Rob and Sergey.
Thank you.
And feel free to stay around and drink our super excessive Stellas or any food. But if not, thank you so much for coming. Really appreciate it. Crushing 2 or 3 beers in a row.
Pretty